So one of the first things you talk about in a calculus class is average rate of change. So rate of change is just how one thing changes based on another, and average is that we're looking at that in a way where it may not be consistent over a period of time or whatever it is. Usually we're talking about time in most application questions. So in terms of the math here, our average rate of change so we're just dealing with this first bullet point here, finding this average rate of change. That's what we're going to focus on in this video, this one. But this average rate of change in terms of its calculation is our change in output, and I'll use that little triangle to be delta, our change in output over our change in our input. Typically we use y and x in math classes, though sometimes we'll be using a t instead. Sometimes y will change depending on what our outcome is. And then of course we could even go into this like y2 minus y1 all over x2 minus x1. So hopefully we're seeing the same thing we talked about today in class, that this is our slope. So our slope is an average rate of change. When we are dealing with a linear function, that average rate of change is the same. It's constant throughout the entire thing, but that's not always the case. And then if we want to get into the function notation that we introduced today with our Desmos activity, now we're saying, well, what was the output for x2 and what was the output for x1 all over our x2 minus x1. So nothing new here in terms of knowledge. We're just going to start using this term average rate of change to talk about things where slope isn't necessarily the word we would use, right? Slope only really applies to a line, and we're going to be talking about average rate of change for any function. It doesn't have to be linear. So there are three ways to, well, four really, but three ways that we are going to talk about functions. We're going to, or display functions. We're going to see them graphically. We're going to see them in a table, which you'll sometimes hear called numerically. And then we will also define them algebraically, which is with their formula. So three different ways to talk about a function. I want this to get bigger, but it's not going to let me. There. Three different ways to talk about a function. So for all of these different methods, we can find this average rate of change, and it's pretty similar how we do so. So let's say for the graph that we wanted to find the average rate of change in this velocity, average rate of change of the velocity, and let's choose between two values we can actually see on this graph. Let's say we wanted to go, looks like 45 is at an obvious place and so is 15. So we could say between 15 and 45 seconds. And we can see there are periods here, just glancing at this. There are periods where our velocity is increasing. There are periods where our velocity is decreasing. But we don't really care about that right now. We're just saying what's the average rate of change. So again, average rate of change you can think of as your slope. What is the slope between these 2 points? As long as you've got that, you realize, well, our average rate of change is going to be positive. We could just do that count over, count up type deal, the rise and run, or we could use one of those formulas from the previous page. So looking here, it looks like our rise, we went from 30 up to 60, so we rose 30 feet per second. And our run, we went from 15 to 40, so another 30, this time in seconds. So now let's go ahead and put units here. It's going to get us good practice for moving forward. So according to this, it looks like the average rate of change between those two values in our velocity is going to be our change in our output, our rise, 30 feet per second, over the change in our input, which was our time, so 30 as well. And so our final answer here, we get 1 feet per second, which is a little bit weird, but trust me, things will be worse when you get into calc. And again, we could have done this using the formula, and we'll do that on the next page, or the next example. So the next example asks us to do the exact same thing, but now we're in a table. And let's go ahead and just answer the same question. So if we want to know that average rate of change in that velocity between 15 and 45 seconds, we already know the answer, but we can double check using our beautiful formula. So in this case, we're doing V of 45 minus V of 15. If you reverse the 45 and the 15, it's okay. You're just going to get negative answers for your change in velocity and your change in time, and they'll cancel each other out for a positive overall. And then our change in time. So there's our change in velocity over change in time using function notation. And in the table, we can see when time is 45, we're at a velocity of 60. So we have our 60. And when time is 15, we're at a velocity of 30. So 60 minus 30, all over our 45 minus 15. That's our y2 minus y1, our x2 minus x1. Still going to end up with 30 over 30, or a 1. And again, we have to think about these units, which I didn't put on there. This is going to be feet per second squared, or feet per second. So, already feeling good about this, hopefully. All the really important thing was the average rate of change is basically slope between 2 points, and we can ignore everything that's happening in between those 2 points. And same thing happens in terms of the algebraic way when we're given the actual function itself. So our last question here says, find our average rate of change. And by the way, I stole every one of these questions from a calculus book, so none of these are even pre-calc questions. And this time it's saying on this interval. So same idea of saying between two values to say on this interval. And so if we wanted to use our notation again, we know we've got f of that pi over 2 minus f of 0 are two different endpoints. You'll notice that I reverse them, but again, that's just so that I can have them end up nice and get a positive change in my x on the bottom. If I change them up, it's going to be okay. I just need to make sure that whatever I have above matches up in terms of the inputs and outputs. And then we're going to have to figure out what these values are. Now it's been like a hot minute since we did any sort of trig, but we've got it. First one is asking me to find the cosine of 2 times this input, which is pi over 2. There's my dot. Sorry, it's been very slow. Minus cosine of 2 times 0. I want red. Sorry, very inattentive about my cute notes. So this is asking for cosine of pi. This is saying cosine of 0. We have to know a little bit about our graph or our unit circle or however we do it. I always think back to the graph. Cosine is the graph that starts at 1 and then goes down. So this is 1 at 0. And then pi over 2 is when we're at 0. Pi is when we're at negative 1. So we are at negative 1 minus 1. This whole numerator is negative 2. Oops, let me move my face out of the way. And this is all over, right? Our denominator here has been pi over 2 the whole time. So negative 2 divided by pi over 2. And if I do a little bit of fraction math, I'm going to get negative 4 divided by pi. That is my average rate of change. And let's go ahead for a second. I'll pause. I can figure out where my pause button is. There she is. I wanted to bring us in a visual. So I'm pulling up Desmos. I typed in cosine of 2x. I'm going to go ahead and change this up a little bit. I'm going to zoom in. I'm going to go ahead and have my y-axis. I know that cosine's range is negative 1 to 1, so let's just do negative 2 to 2. And then let's have our y. It looks like we wanted to know between, what was it, 0 and pi over 2. So let's go from 0, let's do negative pi over 2 to positive pi, so that we can kind of visually see what's going on here. Now, we found a line, right? We found a slope, an average rate of change, not necessarily a line. So what we did today in class, right, is we actually found the equation for a line, and we figured out that we can just plug in a point. And we know one of these points is going to be 0, 1, because we were looking at these 2 points, 0, 1, and pi over 2, comma, unless I got my trig wrong, negative 1, right? So those were the 2 points between 0 and pi over 2. That's where we wanted to know that average rate of change. So right now we think that slope is negative 4 over pi. So if we wanted to check that, we can go ahead and graph that line. Negative 4 divided by pi. Now, of course, this is just a line with the slope. It's not in the right place. So if we wanted to put that in there, we need to use one of those 2 points, and we can use our point slope form. We could say y minus 1. And then I could do, I'm going to use that point slope, so I'm going to just pretend like I don't even recognize that I need that. So we can see we did create a nice little line that goes through those 2 points and has that slope. So that negative 4 over pi is the correct average rate of change. I just want to always bring in the idea that anytime you're doing algebra by hand, you should be using Desmos to look and see that the graph is doing what you expect. And if you're not sure what the graph is supposed to do, ask me, because we should understand how all of these 3 things, the graph, the table, and the algebra, are all interrelated to each other. So there are some more challenging questions here if you want to tackle them. I'll put this into a second video because I'm already getting a little long. But I've got 3 questions. One that's pretty straightforward. 2 actually that are pretty straightforward. One using the algebra, one using the table. And then one that introduces a piecewise function. So if you want to see something a little more challenging, stick around.